Good morning, friends. I feel very happy to be here again for my course Engineering Thermodynamics. I am in the process of problem solving exercise related to entropy change of ideal gas. In my previous lecture also I have taken the three problems. All the three problems were related to the entropy generation with the piston and the cylinder and some other processes. We have seen at constant temperature, at the constant pressure, how much entropy was generated. This we have seen from last problem. In today's problem, I am going to discuss entropy change of the ideal gas issues. So in this, I will be discussing the first numerical, that is entropy change of for ideal gas. The second one is isentropic compression of air in a car engine. Numerical 3 is isentropic compression of an ideal gas. So, in my previous lecture, I have discussed the entropy change during an isothermal process in which the temperature was remained constant, the variation of the pressure and the volume was observed, and we have solved the one numerical in this issue. The second numerical which we have solved about entropy generation during the heat transfer. If the heat is going in, what will happen? If the heat is extracting out, what will be the effect on entropy? This also we have discussed in our last class. Numerical problem 3, that is entropy change of a substance in a tank. If there is a tank, and how much change of entropy of a closed container, that is a control mass system, we have discussed. So now I am taking the numerical one, that is the entropy change for the ideal gas. So this is the problem which I am going to read out here. Air is compressed from an initial state of 100 kilopascal and 17 degrees centigrade to a final state of 600 kilopascal and 57 degrees centigrade. Means the state 1 and state 2 are given. What we have to do? Determine the entropy change of air during this compression process by using A, property values from the air table, and B, average specific heat. So we have to use the table and then we have to use the equations for this problem. So here we can see that the solution for this problem, the entropy change of air is to be determined by using tabulated property values and also by using average specific heat. Assumption here, air is ideal gas. So here we can see the problem statement here. This is the state 1 here. State 1, and here we have the state 2. So here is the compression. So from P1, this is the atmospheric pressure and the temperature is also nearly atmospheric, somewhere some 17 degree centigrade plus 273, it becomes 290. It is entering inside and the compressor is driven and it is compressing to 600 kilopascal, means 6 times, compression ratio is 6, T2 is equal to 330 Kelvin. If you draw in the TS diagram, so this is the P1 and this is the P2, both are not the parallel, they are diverging. So here P1 is 100 kilopascal and P2 is 600 kilopascal, and this is going from 1 to 2. This is the process which is shown here. The properties of the air are given in the air table. Reading S values at a given temperature and substituting, we find that S2 minus S1 is equal to S2 initial minus S1 final, and the initial minus R ln P2 by P1. This is the equation for this S2 minus S1. So we can see here that the S2 from the table, S2 naught and S1 naught 1.79783 and S1 is equal to 1.6680 to 2 minus R is equal to 0.287 kilojoule per kg Kelvin, ln 600 kilopascal divided by 100. You will get minus 0.3844 kilojoule per kg Kelvin. So this you got the entropy, change in entropy, that is the delta S, you got minus 0.3844 kilojoule per kg. Now we have to see another case. The entropy change of air during the process can also be determined approximately from equation by using a Cp value at the average temperature of 37 degrees centigrade from table and treating it as a constant. So Cp we have to find out that. So here Cp minus S2 minus S1 is equal to Cp average ln T2 minus T1 minus R ln P2 by P1. So here this Cp value we have to take as in a given temperature. So here we can see this Cp of air is 1.006 kilojoule per kg Kelvin ln 330 Kelvin divided by 290 minus 0.872 kilojoule per kg Kelvin ln 600 kilopascal divided by 100 kilopascal. So this is here direct from the equation of this one, which we have to put the value, and we will see that how much difference we are getting. So here we will get that 0.3842 kilojoule per kg Kelvin. So is it both are same? Here 3844. How much we are getting here? 3842. Very small, very small, very small difference was observed in both the cases. Okay, so that is the two results are above are almost identical, since the change in temperature during this process is relatively small. So here we can see here that air T1 is equal to 290 Kelvin, T2 is equal to 330 Kelvin, S2 minus S1 is equal to S2. These things which we have already done, it is just as a window it is shown here. Now I will go for the next problem, that is the isentropic compression of air in a car engine. Air is compressed in a car engine from 22 degrees centigrade and 95 kilopascal in a reversible and adiabatic manner. If the compression ratio, that is V1 by V2 of this engine is 8, determine the final temperature of the air. So in this, what is given? The T1 is 22 degrees centigrade and P1 is, this is given, going to a reversible adiabatic manner. If the compression ratio is 8, determine the final temperature of the air. So just we have to put this equation here. So here air is compressed in a car engine isentropically for a given compression ratio. The final air temperature to be determined. Assumption: air can be treated as an ideal gas. So here this we can see that isentropically. So V1, this is the V1 line and this is the V2 line. V1 by V2 is given and this is from 295. It is given here. P1 is equal to 95 kilopascal. T1 is equal to 295. V1 by V2 is equal to 8. These things are given as shown in this diagram. For a closed system, V2 by V1 is equal to V1 by V2. V2 by V1 means it is a specific value and this is the value. So V2 by V1, if it is a closed system, this will be the equal to the mm. So here m V2 by m V1, mm cancel, you will get V2 by V1. So capital V2 by V1, that is the volume of the system, is equal to, the ratios will be same because mass will be cancelled, being it is a closed system. So here T1 is equal to 295 Kelvin, VF1 is equal to, VR1 is equal to 647.9. So VR2 is equal to VR1, V2 by V1. So this we can write, this VR1 is and 1 by 8, V2 by V1. So this VR2 is equal to 80.99, and from this we can get T2 is equal to 662.7 Kelvin. So from here we can find out this is the 662.7 Kelvin. This is the T2. Okay. So this from V2 we can get the T2. Therefore, the temperature of air will increase by 367.7 degrees centigrade during this process. So 662.7 minus 295.0. So you will get 367.7 degrees centigrade. This much temperature will be increased during this process. Now I am going for my last problem for the lecture, that is the numerical number 3, that is isentropic compression of an ideal gas. Helium gas is compressed by an adiabatic compressor from an initial state of 14 psi and 50 degree Fahrenheit to a final temperature of 320 degree Fahrenheit in a reversible manner. Determine the exit pressure of helium. So we have to find out the P2. Okay. So if you see here, P1 is given 14 psi. T1 is equal to 510 Rankine because we have added it. Here T2 we got the 780 Rankine, and we have to find out the P2, and this is the compression. So if we draw here T and S diagram, so it is a isentropic process, the compression from 1 to 2. So how to find out this we are going to discuss here in this problem. So helium is compressed from a given state to a specified pressure isentropically from 1 to 2 as shown in this diagram. Here we have some assumptions. At a specified condition, helium can be treated as an ideal gas. Therefore, the isentropic relation developed earlier for ideal gases are also applicable for this helium also. Analysis, a sketch of the system and the TS diagram of the are shown in this figure. The specific heat ratio K for the helium is 1.667 and is independent of the temperature in the region where it behaves as an ideal gas. So as and when we are assuming an ideal gas, the ratio of Cp by Cv is equal to gamma, and this gamma, this is also called the gamma, and gamma is equal to 1.667, and it is a constant. Thus the final pressure of the helium can be determined from the equation of the ideal gas. So we can see that P2 by P1 is equal to T2 by T1 gamma by gamma minus 1. So here P1 is equal to 14 psi and T2 is equal to 780 and P1 is equal to 510. So we will get P2 is equal to 40.5 Pascal psi, pound per square inch. So we got here P2 directly. There is no problem in this. Here I have taken, so if you see in this very simple problem, it is not a very big issue. Directly we can put the relation of isentropic process in this isentropic, we know the relation P2 by P1 is equal to P2 by P1 is equal to T2 by T1 gamma by gamma minus 1. And this, all the three values are given. We can find out the next value. These, the references which I have taken, only the Eunice Senegal, that is Thermodynamics and Engineering Approach, McGraw-Hill's 7th edition, very good book. Any questions you are welcome to ask. My email ID is ydwidi@gmail.com. I request you to like and subscribe. If you really like my channel, try to like it and try to subscribe it. If you feel anything, you can comment on the comment box. It will be very useful for me to improve myself. Thank you very much for the joining. We will see for the next lecture very soon. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.